Great. Thanks so much for the introduction. Thanks everybody who's here or on Zoom. I know I'm the only thing standing between you and a long weekend, so I'll try to be concise. So I'm going to be talking today about efficient OCR for building a diverse digital history. This is joint work with Jake Carlson, who's a grad student here in the economics department at Harvard, and Tom Bryan, who's a pre-doc in my lab. And so digital texts are central to the study, the dissemination, and the preservation of human knowledge. Tens of millions of users consult digital archives every day, but many billions of documents remain trapped in hard copy in libraries and archives around the world. So for example, the US National Archive has something like 14 billion hard copy documents. These documents contain extremely diverse character sets, languages, fonts, handwriting, printing technologies, and artifacts from scanning and aging. Digital texts are incredibly valuable. They allow for automated indexing and search, for computational textual analyses, for statistical analyses, for training large language models, and for easier consumption of the material in them by researchers and also by the general public. All right. So mass digitization of documents trapped in hard copy requires an OCR that will be highly extensible to novel settings. There's lots of diversity in historical documents. It needs to be accurate, especially if you want to use this to do statistical analyses, even for large language model training, et cetera. And it needs to be very, very cheap to deploy because there's billions and billions of pages of scanned documents. And OCR oftentimes falls short of these goals. Poor performance on historical documents is widespread. That's not why most OCR products were designed. They were designed to do commercial applications like OCRing receipts. And so there's been an enormous post-OCR error correction literature. And this has also skewed digital history towards limited settings that are not representative of the diversity of documentary history. So in the history department here, people spend a lot of time talking about how the people who leave behind documents aren't representative of humanity, which is certainly true. But that problem gets magnified many times over when you look at what's actually digital and accessible, because digital documents are very concentrated in high resource languages like English, for example. And so for instance, a document collection that was of interest to us, which are printed Japanese documents from the 1950s. So this is nothing too crazy. They're not that old. They're printed. But the best performing existing OCR mispredicts over half of characters. So I cannot take that and run regressions with the output. It's just basically garbage. This disappointing performance is at least in part the result of the predominant architecture used for OCR, which was not designed with the objective of digitizing the world's documentary knowledge. And so OCR is typically modeled as a sequence-to-sequence problem. What that means is that learned embeddings from a neural vision model are taken as inputs to a learned language model. The sequence-to-sequence architecture is challenging to extend and to customize to novel settings because training a vision language model takes a vast amount of data and compute. Even for high resource settings like English, it is really costly to train or tune open source seek-to-seek OCR alternatives. And so what we've done is to develop a novel open source OCR architecture called efficient OCR, or FOCR for short, which is designed for researchers and archives who are seeking a sample efficient, customizable, and highly scalable OCR solution for diverse document collections. And so FOCR tries to come full circle, going back to the simplicity of the first OCR systems in the 1920s, but combining that with deep learning. And so what FOCR does is to bring OCR back to its original roots, which is the optical recognition of characters. FOCR is central to a broader suite of digitization tools that my lab is developing or has developed. We have an open source package for document layout analysis called Layout Parser. We have some packages for record linkage, so link transformers, which is using transformer large language models to do record linkage and other data wrangling tasks in an easy to use interface. We have a package for visual record linkage for CJK. And we're doing various work on NLP for information extraction. All right, so now I want to delve in and explain the FOCR architecture and what makes it particularly well suited for digitizing large-scale, diverse document collections. Modern OCR overwhelmingly uses deep neural networks, either a convolutional neural network or a vision transformer, to encode images as dense vectors. And these vector representations, which are created by passing the input image through a neural network, are then decoded into the associated text. So seek-to-seek architectures typically require text line level inputs, and they don't localize individual characters. Rather, images or their representations are divided into fixed size patches. In contrast, FOCR starts by localizing characters or words using modern object detection methods. Another important difference between FOCR and standard seek-to-seek OCR is that seek-to-seek sequentially decodes learned image representations into text using a learned language model that takes image representations as inputs. So this is a language model that's taking images, not tokenized text, as inputs. So you can't just take a pre-existing language model and use it because you're not taking tokenized text as inputs. And this is part of why learning seek-to-seek OCR is so costly, because you are training a large language model as part of it, in addition to a vision model. In contrast, FOCR recognizes text by learning meaningful representations of individually localized character crop images. So crops of the same character, regardless of style or font, are mapped to vectors that have high cosine similarity. Crops of different characters are mapped to vectors with low similarity. And these character representations are decoded into text in parallel, not sequentially, which has an inference speed advantage, by retrieving their nearest neighbors from an offline index of character image representations created from a digital font. And so I want to make this a little bit more clearer by showing you a visual comparison of our architecture versus seek-to-seek. And so FOCR is first of all going to localize characters, and then it's going to encode those characters such that the nearest neighbor to that character in the offline embedding index is the text that it represents. Whereas seek-to-seek is not locating individual characters, it's dividing the text line image into patches and encoding those and then decoding them using a learned language model. And so this is an example of a CRN architecture. It uses a CNN and an LSTM. There's also versions of seek-to-seek that use transformers, both the vision and language model. So you can see, again, another kind of representation of the architecture. Okay, and it's not localizing characters. It's dividing it into patches and then decoding the feature sequence that comes from the CNN or from the vision transformer. All right, and so one advantage of the FOCR architecture is that it's very straightforward to swap in different vision encoders for both the localization of characters and the recognition of characters. And this helps to future-proof FOCR, because if there's a model that comes out today that's better, it's easy for us to swap it in. And so we use 3 state-of-the-art vision encoders in the paper. We use a vision transformer model called Excite, which is our base transformer model. We have a convolutional base model, and we have a convolutional small model, which uses lightweight architectures that are designed for mobile phones and therefore is very cheap to deploy. So far I've been talking about recognizing characters. You might say, well, why recognize characters and not words? We recognize words as well. So instead of localizing and recognizing text at the character level, both of those things can be done at the word level. You know, for a language like Japanese, it's the same thing because characters are words, but obviously for a language like English, recognizing words makes a lot of sense. And so our optical word recognition model learns a metric space where images of the same word, regardless of style, have similar vector representations, just like with characters, but now with words. Similarly, at inference time, words are recognized by retrieving their nearest neighbor from an offline index of word embeddings that are created with a digital font. You might say, well, how can you have a comprehensive word index? Of course, it can't be comprehensive. You have proper nouns, you have acronyms, you might have hyphenated words at the end of a line. And so what our word recognition does is if the embedding of the word is below a threshold cosine similarity to the nearest embedding in the offline index of words that are created with a digital font, we default to character level recognition. And so we can handle words that aren't in the dictionary with ease. We train our word recognition model primarily on synthetic data. And again, it's highly extensible because it only needs to visually recognize words. It doesn't have to learn how they're used in sequence. And so if you want to use it for a language for which there is no transformer large language model, that's not a problem. It uses lightweight models designed for mobile phones, and it's nearly 50 times cheaper to deploy than a popular sequence-to-sequence alternative with similar accuracy. And we have deployed this model to cheaply and accurately digitize around 20 million public domain historical newspaper scans. Okay, so I'll just give a few more details about the models. And so in some sense, I'm talking about base models and small models, but actually all these models are pretty small by deep learning standards. So for our base convolutional model, we use ConvNext. And we also have a model using the Excite vision transformer. And our small model uses YOLO v5 and MobileNet v3, which are designed for mobile phones and are just very, very cheap to deploy. We also examine oblations with other vision transformer models, so SWIN and VIT.base. All right, so why did we choose these encoders? Well, ConvNext is a state-of-the-art CNN, and we wanted to see how CNNs would do. We chose Excite because it has linear complexity attention, which allows us to use a small patch size, which you might think would be useful for recognizing characters in a document that has lots of characters in it. They might just be a few pixels wide. And we chose MobileNet and YOLO v5 because they're very efficient. Object detection backends, again, advantage of the modularity of FOCR is it's easy to swap in different object detection backends depending on what your objectives are. And so we use Cascade our CNN via detection for our base models. We use YOLO for our small models because it's very efficient to deploy. And we also have Detectron 2S and Oblation. And these are all supported by our package. And so again, users of efficient OCR have a lot of flexibility to use different object detection backends because we have this modular, simple architecture. We do hard negative mining, so every character crop that appears in the training set is embedded using a model that's trained without hard negative. And then we find 8 nearest neighbors of each of those, and we intersperse those hard negative sets into our training batches. Data augmentation is an important part of this framework. We did really minimal labeling for this. Most of what the model is learning from is seeing different digital fonts. And so our main data augmentation is just the use of multiple fonts. We use 43 different fonts for English, and I think 13 different fonts for Japanese. So while fonts and a small amount of labeled data are kind of our main data, we also do additional data augmentations, random color jitter, random auto contrast, Gaussian blurring, et cetera, kind of standard image augmentation transformations in order to get kind of additional variation in the data. All right, so as our objective, we use a supervised contrastive loss function. So what SupCon does is allow you to have multiple positive and negative pairs in a batch, and this is really useful because with our strategy of learning characters from mapping different digital fonts to similar representations, that automatically gives us multiple positive pairs in a batch, right? Because we have dozens of digital fonts. And so we use a SupCon loss function. And so essentially what this loss function is doing is representations of the same character but in different fonts with different data augmentations should be mapped to the same embeddings, and representations of different characters should be matched to different embeddings, or should be mapped to different embeddings. All right, so that's an overview of the architecture. I want to say a word about how we evaluate this. And so OCR benchmarks are, the main widely used ones are receipts because that is the main commercial application. And we are an academic lab. We really don't care about digitizing receipts. We care about digitizing historical documents. And so we needed to create our own benchmarks. And this was a big part of the, the work of this paper, right? Because now that we have our own benchmarks, we have to get every other model out there and whatever their code base is to run on our benchmarks. But we did that to have fair comparisons. And so what are our benchmarks? Well, first of all, we choose an Asian language. We choose Japanese. And we draw on documents that can elucidate fundamental questions that have been understudied in economics due to a lack of digital data, such as the drivers of Japan's rapid transformation from a poor agrarian economy at the beginning of the 20th century to a wealthy industrialized nation. We have horizontally and vertically written Japanese tables as well as prose. And these texts could use over 13,000 different characters. We have a second very different benchmark, which is historical newspapers from the US that are taken from Library of Congress's collection of historical newspapers. And Library of Congress does provide an OCR, but the quality is very poor. So we do this for several reasons. We want to see how we do in the highest resource setting, which is English. And we want to see how extensible the model is across Latin versus kanji characters, which differ significantly in their aspect ratios and complexity. And it's also the case that many endangered languages that are renderable with Unicode use the Latin script. And so since this is just using characters' visual appearance, it's not using language, these results that we get would be extensible to these endangered languages that currently, like you seek OCR just can't handle them because we don't have large language models for those languages. So this is an example of what our document collections look like. Here you'll see our labeled training sets, validation, and test sets. And you can see these numbers are pretty small. So this is what these are the actual target characters that we're gonna show the model. We do not train on much actual data. Most of what we're doing is with synthetic data. So you can think of the results, I'll show you almost like few-shot results. We also create another labeled data set for the historical US newspapers, which is more difficult. So we sample random lines per decade starting in the 1860s. And some of the stuff from the 1860s, I mean, you can see that this is like pretty challenging. So when I say OCR in historical documents, I want you to have in mind, what I mean. We also examine zero-shot performance. So we're going to take a model and we're going to tune it on a modest number of labeled crops from historical newspapers, but we want to see how that does in general. And so we're going to randomly select documents from different record groups in the National Archives. We digitize those, and then we're going to see how we do totally zero-shot. And again, like you can see that these have lots of weird artifacts. They got handwriting on top of the text, and this is a challenging setting. So we're going to see how we do completely zero-shot on documents that look like this. All right, so we measure OCR accuracy using the character error rate, which is just the Levingston distance between the OCR string and the ground truth, normalized by the length of the ground truth. So if you have a character error rate of 0.5, you're getting approximately half of the characters wrong. And we're going to do a variety of comparisons. We'll compare off the shelf to Google Cloud Vision, which is proprietary. We don't know what it does, but it's the leading commercial solution, to Baidu OCR, which is also proprietary and is very popular for Asian languages, and to Tesseract, which is a popular open source alternative that uses a CNN and a bidirectional LSTM. We'll also compare to models that are fine-tuned or trained completely from scratch. So Easy OCR, Microsoft's TROCR, which is a sequence-to-sequence encoder-decoder transformer model, and Paddle OCR, which, like FOCR, uses only vision, but does so with a different architecture that doesn't recognize individual characters. So these are all three popular state-of-the-art open source OCR engines. They're widely used either because they're cheap to deploy, like in the case of Easy OCR, or they're really accurate in the case of TROCR. So we're going to compare to these as well. So we have a variety of different comparisons. First, we can train everything from scratch on the same target data as FOCR, and so that's the most apples-to-apples comparison. Huge amounts of resources went into training these different OCR engines. So for example, for TR-OCR, it was pre-trained by Microsoft on 684 million English synthetic text lines. And so we can take what already exists, they already had a lot of resources go into them, and then we fine-tune on our target data and see how that does. And that's more the practical comparison. It's not an apples-to-apples comparison of these architectures, but practically, if I have a lot of documents I want to OCR, I want to know, okay, should I mess with OCR? Should I fine-tune one of these other alternatives? And so we do those comparisons as well. And then we look at them also zero-shot, which is in reality how most people use OCR engines. Okay, and our baseline results, and so we have these 5 different samples that we evaluate on. And you can see for the Japanese tables, whether written horizontally or vertically, our character error rate is well under 1%. And I'm going to show you in a minute the next best alternative for the vertically written Japanese tables gets over half of characters wrong. And so basically, for these Japanese documents, FOCR is producing something that's nearly perfect on minimal target training data, whereas most other existing solutions would be unusable, especially for the vertical Japanese. On the newspapers, we do pretty good. So with the word level model, which is our preferred one, the character error rate on our main data set is 1.5%, and on the more difficult data set that goes way back to the 1860s, we get about 4% of characters wrong. And so when you look at the errors that FOCR makes, it's making errors of characters that look quite similar to each other, what we would call homoglyphic errors, confusing characters with similar visual appearance. The same thing is true for Japanese, and you can see why this is such a difficult task. These are different characters. The nearest neighbor, the one on the left, is the correct one, and the one in the green box is the error that we're selecting, and you can see they look very, very similar, and the underlying quality of the documents isn't necessarily great. So when FOCR gets it wrong, it's pretty hard to get right. These are our comparisons. So these are the off-the-shelf, most widely used OCR engines. And on Japanese, they're pretty unusable. On English, Google Cloud Vision is actually great, but I'm going to tell you in a minute there's a catch. It's proprietary, and it's very expensive. And then when we look at the other open source OCR engines, whether we're using them off the shelf, fine-tuning, training from scratch, they all do not that great because FOCR is more sample efficient, which I'll come to in a minute. When they're fine-tuned, the only thing that's really competitive is TR-OCR, which is this large, 330 million parameters, something like that, sequence-to-sequence transformer model. And it's getting pretty similar accuracy to our 11 million parameter lightweight model. And so deployment. In practice, what will we use? So you saw that for English, Google Cloud Vision was the most accurate, but unfortunately it makes significant layout errors when fed full newspaper page scans, which tend to have complex layouts. And so the performance I showed you isn't replicated unless you give it individual lines. And Google Cloud Vision unfortunately charges per image, and so to give it individual lines would mean that the cost to digitize the Chronically in America collection that we'd like to digitize would be $23 million US. Okay, I got a grant for $60,000. It has to be done within $60,000. I don't have $23 million, okay? So that's just out of the question. TR-OCR was comparable, a little bit better than FOCR, but it's about 48 times slower. So that's also a really big problem for my $60,000 budget, and probably for any budget that a library or an academic or an archive is going to have. So FOCR is just very fast. It's using very lightweight models, and it supports inference parallelization across characters, where seek-to-seek requires autoregressive decoding of the sequence, and so it's much slower. On English, the most plausible scalable alternative is fine-tuned easy OCR, but it's slightly slower and significantly less accurate. For horizontal Japanese, FOCR is 3 times more accurate and faster than paddle OCR. which is the next best alternative. And for the vertical Japanese, there's just the open source packages don't support vertical Japanese, and so there's just no alternatives besides FOCR. And this is just showing the inference speeds that I mentioned. Okay, well you might be saying, what about ZeroShot Performance? So you've shown that this does a good job on newspapers. It didn't see that many labeled examples, but it saw some labeled examples from the target data. And so to test how it does on ZeroShot Performance, we select a single text line from each of 300 random documents, all from different National Archives record groups. And so this is a really heterogeneous sampling of historical documents from the US National Archives. FOCR achieved a character error rate of 11.2%, which is pretty much in line with what you get from using Tesseract, BEST, or Easy OCR. And actually, TROCR small really struggles. Base does better, but it's very expensive to deploy. And Google Cloud Vision does better, but as I said, it's very expensive. And so we didn't design this to be a zero-shot, performer, and this is something that we're working on, making it better zero-shot. But even without trying to make it work zero-shot at all, it only saw digital fonts and some newspapers in training, and then when we use it on this really diverse historical document collection, it's kind of in line with the other open source alternatives. And we suspect these results could be made significantly better just by giving it a few shot exposure to diverse document collections, maybe by doing more with our synthetic data augmentation. But even without kind of trying to make it perform well zero-shot, it's doing pretty decent. Okay, sample efficiency. I think this is really at the heart of what FOCR contributes. And so FOCR has a vision-only architecture. It's just learning the visual appearance of characters or words. And that allows it to learn very effectively with little training data. Just like children can learn their alphabet before they learn to read, it's easier to learn the visual appearance of characters than how they are used in sequence to form language. And so to quantify this, we compare FOCR base to leading open source architectures that are pre-trained from scratch on the same number of synthetic text lines as FOCR, and then fine-tuned on the same target crops. And we find that on as few as 99 labeled table cells for Japanese and as few as 21 newspaper column rows, which is really a tiny, tiny sample for the newspapers, FOCR's character error rate is only 5% for the Japanese and 7% for English. And so this really has what kind of looks like good few-shot performance. And so this is sample efficiency. The yellow and the green are TROCR, which is a sequence-to-sequence transformer model. And it just can learn nothing from the amount of data that we train FOCR on because it's a sequence-to-sequence transformer model, and we know transformer language models are going to take a lot of data to train. The smaller, older OCR architectures using CNNs and RNNs are kind of doing a bit better. They don't need quite as much data to learn from, but FOCR is still much more sample efficient. We hypothesize that it has lower sample complexity than vision language seek-to-seek models. Okay, we also do some oblations. We do OCR as a nearest neighbor retrieval. That does a bit better than doing it with just a standard feed-forward neural network. It also allows it to be really fast because we can use an FAISS backend. If we turn hard negative mining off, we don't do as well. Hard negative mining is important. With synthetic data, it's kind of interesting because for Japanese, you do horrible without the synthetic data because we don't label that many characters, and many of the characters that appear in our test set don't even appear in our train set, right? So you really need the synthetic data. For English, there's not that many letters, and so you do a bit better when you don't have synthetic data. And kind of the opposite is true for localization. English characters have lots of different aspect ratios. Japanese characters are almost always squares, and so they don't need the synthetic data as much. And finally, we explore some other encoders that show similar results. I think it's kind of interesting that all the different encoders give pretty similar results. It's like these very different architectures are able to all learn the problem quite well. Okay, and so we've actually used FOCR to liberate data at scale. So we've used it to cheaply and accurately digitize the nearly 20 million page scans in Library of Congress's Chronicling America collection. We use a custom layout model to first recognize individual layout objects on the page, like articles, headlines, bylines, captions, etc. We classify and remove illegible content, and the resulting output consists of accurate, structured article text for headlines, articles, captions, etc. And so this is showing our pipeline where we detect the layouts, classify legibility, OCR the text, and we also associate articles with their headlines. This is our non-word rate of our OCR compared to the Chronically in America OCR. And you can see that there's far fewer non-words in our output. That could be for a variety of reasons, or architecture, the fact that we filter out illegible content, which is an important part of providing high quality content. Of course, we expect some non-words because there's acronyms, there's proper nouns, there's hyphenated words at the ends of lines, etc. But overall, this shows that we provide high quality text. Accurately OCR'd structured article text open the door to many different applications, some of which we show in the paper. And so named entity recognition and entity disambiguation can be more accurate when you have structured text. We show in the paper that topic classification tends to be more accurate with our structured text than with the existing OCR, which has far more errors and doesn't recognize the layouts. Also, we can do text classification at the article level. We can better detect reproduced content. And as kind of a fun example of things you can do once you have these structured article text that you couldn't do with Library of Congress's OCR, which just scrambles up all the text on the page, we determine stories, and we see which stories are most printed across time. And so specifically what we do is we train a custom large language model to map articles about the same story to similar representations and articles about different stories to different representations. And then we use single linkage clustering to take the representations from these literally hundreds of millions of news articles and cluster them and see each year what's the biggest story. And I thought that this was pretty fun. Some of it's a little depressing maybe, but you see kind of what you would expect to be the biggest story of the year, I think, but also maybe some insights. You see lots of rail strikes, conflicts, et cetera, Pancho Villa expedition. All right. And so overall, the American Stories data set contains 1.14 billion content regions and includes over 438 million articles. As I said, we could do this with our $60,000 budget that I managed to get some fund in the economics department to give me, so really done on a shoestring. A lot of content for that budget because the OCR is so efficient. The data is available for download on Hugging Face. And the paper has lots of applications. And this is joint with a big team of awesome people, Jay Carlson, again, and Tom, who are on the FOCR paper, also Emily Silcock, Abhishek Arora, Zijing Shen, Luca de Amico Wong, Quan Li, Pablo Carabin, and Leander Heldring. All right, another example of how we can use FOCR to liberate data at scale. We've been using these to take Japanese historical firm-level publications and turn them into a knowledge graph that provides rich information about network relationships in the historical Japanese economy. So these relationships can be observed through shareholding patterns, family ownership, financing boards, occupational histories, family connections, spatial locations, supply chains, combined with rich financial production and biographical information. Japanese individual and firm names are often just a few characters long, and hence you do need a really good OCR to do this, because if somebody's name is 3 characters wrong and you get one of those characters is 3 characters long and you get a character wrong, you're not going to be able to figure out who they are. And we just could never have done this with the existing OCR. And so this is just an example of supply chain networks. And so here each node is a firm. And the size of the firm is proportional to its degree centrality in the supply chain network. And then the shading represents firms that the US occupation tried to break up. So they tried to go in and do some antitrust, but basically what you can see is that the biggest firms in pre-war Japan that they tried to break up remained the most central firms in the supply chain network in the 1950s. And so basically this policy did not succeed in breaking up the largest firms. And this is just an example. There's lots of other things that you can look at with these data. All right, So I want to briefly discuss the key features of FOCR and what we think makes it so useful. And so FOCR, importantly, is designed to encourage community engagement. So indexing, analyzing, disseminating, preserving diverse documentary history requires community engagement of stakeholders who have the requisite fine-grained knowledge of the relevant settings. And if you're using some big seek-to-seek model, it's very complicated to deploy, you're just completely shutting those people out of the question. They don't have the budget for it. It's not suitable maybe to their language because we don't have large language models for their setting. FOCR facilitates this engagement because it's highly extensible to low resource settings, it's sample efficient to customize, and it's simple and cheap to train and deploy. So in contrast, seek-to-seek OCR is more aligned with the commercial objective of designing a product that is difficult for your competitors to imitate. So for example, FOCR can be trained in the cloud with free student compute credits, whereas TROCR, the transformer seek-to-seek model, required training on a multi-million-dollar cluster with 32 gigabyte V100 cards. Lower resource languages may lack the pre-trained large language models required to initialize a transformer seek-to-seek model like TROCR in the first place. And regardless, compute resources and data for training are also likely unavailable. Okay, and so FOCR encourages community engagement by combining a parsimonious conceptualization of OCR from nearly a century ago, where OCR is about recognizing the visual appearance of characters or words with the AI revolution in computer vision, integrating the following features. So first of all, it focuses on characters and words. It only needs to create semantically rich visual representations of individual characters or words, which is a parsimonious problem. This is also an easy problem to annotate for. So annotators can select which of the most probable character predictions from the pre-trained recognizer are correct, potentially using a simple mobile interface. Language extensibility. So language modeling advances have been concentrated around less than 24 modern languages out of many thousands of languages that are important to understanding human societies. And of course, there's benefits to having a language model. If it works well, it would make your predictions less, more, it would enrich your predictions by being able to use the context around it. But in practice, we don't find that seek-to-seek helps a lot, and it comes at a high cost. Omitting the language model makes FOCR extensible, and it makes it much easier and cheaper to train. To extend FOCR to a new language, all you need are image renders of the appropriate character set. And another kind of useful feature of this is that characters don't need to be seen in sequence during training, so new characters can be added at inference time. That's not true with seek-to-seek, and this is really valuable for context and corpuses where new characters are encountered between training time and inference time. And so, for example, this is common in archaeology, right? You have trained a model to recognize the characters that you find inscribed on tablets. And then you go and you dig a new site and there's new characters. You don't want to have to train your model from scratch every time you discover a new character. Even in the stuff we do as economists, we discover there's some weird symbol in this book that turns out to be important, right? It's very common to discover new characters between training time and inference time, and we showed that FOCR handles those very well, whereas you can't have that with seek-to-seek. Omitting the language model makes it easy to mix scripts, which is necessary for some endangered languages. And the recognizer can also be exposed to characters in training using any desired sequencing, which is not true of multilingual seek-to-seek training, which leads to many OCR errors with endangered languages. Okay, another important feature is that we decouple localization and recognition. So theoretically, localizing characters and recognizing them, which is akin to classification, may rely on different features of the image, suggesting modularity. So this is what is known as the sibling head problem. And so because localization and recognition require different features, it can actually be advantageous to do that with different backbones rather than coupling those together. Perhaps even more centrally from a practical perspective, decoupling the localization of characters from their recognition allows us to use different training sets, which economizes on annotation costs since these tasks can require very different number of labels depending on the script and on the language. It also encourages community innovation and future-proofness because it simplifies training recipes and makes it straightforward to swap in encoders as the literature advances, which is something we've already done to an extent. Oh, we saw that there's this new vision encoder that looks really promising. Let's try it out and see how it does. And that's very straightforward to do. We have a beta open source package for inference and training. And I'll be giving more information on this very soon. We're just doing some final testing before we publicly promote it. FOCR sees small and the word level. FOCR achieve fast CPU inference that can scale cheaply to hundreds of millions of documents, potentially helping to cheaply digitize the billions of documents that remain trapped in hard copy. FOCR does have some limitations. We do not focus on handwriting, but the approach would be analogous. So synthetic handwriting generators could provide extensive data for pre-training, analogous to the study's use of digital fonts. And so handwriting is something that we are beginning to work on, but at present, FOCR does not support handwriting because it's, because we started by focusing on print. If large portions of a document are illegible, then language can provide educated guesses. It might also be that you have a very small data set in a high resource language and budget constraints don't really bind, then Google Cloud Vision may be your best bet because it is accurate on high resource languages like English. And if you don't have a binding budget constraint, there might be some other solution that serves you best. The other thing that we want to and are working on is doing more training on a broad diversity of documents for improved zero-shot performance. All right, so I'll briefly mention extensions. So the FOCR architecture is useful for other applications. In particular, OCR tends to make errors that are homoglyphic, confusing characters with a similar visual appearance. So this is obviously true by definition for FOCR because we're doing OCR as nearest neighbor retrieval based on visual similarity. But we also document that it's true for other OCR engines like Easy OCR and Paddle OCR. Together with Xinmei Yang, who is an incoming first-year grad student at Harvard, as well as Xiaoyu Zheng and Abhishek Arora, who are two pre-docs in my lab, we have exploited a similar model to measure visual similarity across different characters and use this to improve record linkage in the CJK script. And so in short, you have two characters that you want to link, two strings that you want to link, but they have OCR errors in them. So how do you do that? Well, if you measure the visual similarity between those two characters, we show that it greatly improves record linkage accuracy over existing methods. And it's very easy. We have a package. It's very easy to use. It's very familiar to people who are familiar with string matching. So maybe if you did an end-to-end deep learning model, which we've also done, it would be better, but it's harder to use, harder to tune. And so by just measuring character visual similarity and then using that as the substitution cost within edit distance matching, you can improve record linkage. And we have an easy-to-use package to do that. And I just want to show one fun example from the paper. So we were mostly focused on, merging historical documents as in, maybe sometime in the 20th century. But we wanted to know how extensible this approach was to different scripts. And so we decided to see how it worked for ancient Chinese. And so this is just sort of a fun example. But we used our character visual similarity, again, using kind of the same methods as FOCR to contrastively train a space on digital fonts. We used this to look at what were the most similar characters to each other in ancient Chinese about 3,000 years ago. So we have an example character. And it's kind of fun because, so the example character is writing, and the closest characters to it are law, learning, also morning, which is recording the sun. We give some other fun examples too. So we have a middle or high level official, and it's close to other officials. We look at the character for history or historian, and it's close to conquest. It's close to city center, which is actually a picture of somebody being executed in the center of the city, to give you a sense of kind of the relationship between history and the state and state capacity. And so this is all just sort of an entertaining example of how, with character visual similarity, and having this space where we can measure character visual similarity with this embedding space, we actually get representations of characters that are consistent with things that people have written in the archaeological literature. All right, so just to conclude, massive quantities of highly diverse documents remain trapped in hard copy. Digitizing them requires an OCR that is simple and cheap to customize and deploy. And FOCR was designed with these objectives in mind, and we hope it will encourage further community engagement with OCR and make it easier for researchers to study a diversity of historical settings.